Well, hello again, everybody. It's that time, exciting math time with your boy McCutcheon. That's right. And today I'm going to be bringing you a video about domains. How do we find the domain of a tricky function, you might be wondering? I know I was. Well, to be honest with you, there are only two things that we need to concern ourselves with. One is the fraction bar. See, all numbers on top, they're okay. It doesn't matter what goes up there, but what's going on the bottom, you might be wondering? I mean, can I put anything I want in the bottom? What about the number 0? Oh my gosh, that's right. You can never, ever, ever have a 0 on the bottom. But what can you have on the bottom? Yeah, anything other than 0. It makes the boys and girls happy. What's the other structure you might be wondering about? Well, my personal favorite, the square root bar. I mean, what's going on underneath that square root bar? I mean, can we just have anything we want? What about, negative numbers? Oh my gosh, yeah, no, you can't have negative numbers underneath the square root bar in the real number system. So what can you have? Well, you can have any number that's greater than or equal to 0. It also makes the boys and girls happy. And that is how we're going to be figuring out what the domains of crazy functions are. If we have a fraction bar, we're just going to set the bottom not equal to 0 and figure out what numbers are trouble for us. And if we have a square root bar, we're just going to set what's underneath it greater than or equal to 0 to figure out what numbers are trouble for us. And what happens if we combine these structures? Ooh, magic ensues. And we're going to get to it here in just a moment. So I went through the textbook and I started pulling questions that I didn't assign for homework because I thought maybe that would be a great place for us to practice with, right? I mean, what better than to practice with things that are just like the homework, because that's what kind of stuff is going to be just on your tests, okay? So I want to make sure that nothing that I show you is a mystery come test review time or even test time. So first example I wanted to take a look at in our textbook was on page 94. You don't need to know that if you don't want to, but that's where I'm finding these things on. Wait, not question 94, page 94, sorry. And I'm actually looking at quick review number 5 right now. The directions were not to write down the domain. The directions were simply to just figure out what numbers would cause a function to not be defined. But I figured we might as well go ahead and get in the habit of writing domains, right? So let's go ahead and write x over x minus 16. So this is a fraction. Yeah, I know there's x's on the top, but who cares? You see, it doesn't matter what's on top. Remember, what makes the boys and girls happy is that the bottom doesn't equal 0, and what makes the pig squeal is if the bottom does equal 0. So this is not going to affect our domain at all. The only thing that matters is that this denominator, x minus 16, does not equal 0. And then we just, quote unquote, solve for x as if this was an equality. We go, okay, well, if we add 16 to both sides, what we're going to get is that, oh, x simply cannot be the number positive 16. That's the only problem that this function has when x equals positive 16. So its domain can be written as all real numbers except for the number 16, which looks like this. Negative infinity, up to 16, union, and then hop over 16 and continue along your merry journey to positive infinity. Boom, there it is. So what if we took that x minus 16 that we were just dealing with and we threw it underneath a radical? Remember, what makes that pig squeal? Negative numbers underneath this radical. They're not allowed. But the square root of 0 is 0, so all I have to do to find the numbers that are allowed to be under this radical is to take what's underneath here, called the radicand, and set it greater than or equal to 0 so we can make those kids scream for joy. Again, just get x by itself, add 16 to both sides, and we get that x must be greater than or equal to 16. Our domain then would just be the numbers that begin at 16 and head towards infinity. Now, it's not in the textbook, but I thought a great thing to see now would be radicals underneath a fraction, or fractions underneath a radical, with specifically this x minus 16. So, made up quick example. What if your function was some x over square root of x minus 16? Okay, first, you do have something underneath a radical. This up here, nobody cares. There are no problems with top numbers of fractions. However, the bottom of a radical, the bottom of a fraction cannot equal 0, and inside of a radical cannot be negative. So both rules have to come into play here, where normally we would have just said, okay, x minus 16 is greater than or equal to 0. We can no longer say the or equal to part, because if x were equal to 16, you would have 16 divided by 0, and that is a big fat no-no. So it's not that it's a separate rule. I don't want you trying to memorize a rule for if there's a radical in the denominator. No, what I want you to do is ask yourself, what kind of rules do radicals come with, and what kind of rules do denominators come with, and just make sure that you're respecting both rules. Simply realize that you cannot say x minus 16 is greater than or equal to 0 anymore, because the equal to part is a big fat no-no. You would just add 16 to both sides, and you would get x is strictly greater than 16. So its domain would be written as the numbers beginning at 16 but not including on up to positive infinity. Well, if we flip this fraction upside down, can x be 16 now? Well, yeah. The reason why x can be 16 is because the square root of 0 is 0. And 0 divided by any number that's not 0, remember, makes the pig squeal down here. 0 divided by any number is always going to be just 0 again. So for this one, you would have to worry about the radical, but you could disregard the don't let it be equal to 0 part, because yeah, it's on the top of a fraction. So now you could say, yeah, x minus 16 is greater than or equal to 0 again. You just have to make sure that you respect the denominator rule as well. This one cannot be 0. But since this is going to restrict us to numbers that are bigger than or equal to 16 anyway, we're not going to have to worry about 0, because 0 is smaller than this. So what if I tweak the question slightly? Let's just keep playing with this x minus 16 and this x. But instead of saying minus 16, let me tweak it for a second and say x plus 16 over x. All right, now remember, we're trying to respect all the rules. So first and foremost, I see a radical. We have to make the kids say, yay! So we take what's underneath the radical, and we say it's greater than or equal to 0. I forgot to write the 16. Goodness. There. And because it's on the top of a fraction, getting a 0 is just fine. We get x by itself. That tells me that x is greater than or equal to negative 16. It's not a problem that this is a negative number. All that matters is that the structure itself is not negative. And then I go, okay, cool, so I can use any number I want. That is negative 16 or bigger. Up. Don't you forget, the bottom of a fraction has a rule. Don't make that pig squeal. This x cannot equal 0. both rules must be respected. I can use any number greater than or equal to negative 16 except 0. So this one's domain would be beginning at negative 16, heading up towards 0, but you're going to have to hop over it with a union, pick back up at 0, and head along your merry way to positive infinity. There we go. And basically, as long as you respect both rules, you're going to be just fine. I figure pull a few more examples from the book and we'll just see where it takes us. How about quick review number 10 on page 94? Again, we were just supposed to figure out what numbers make the function undefined, but I like the whole writing that domain in interval notation setup. Okay, so no radicals this time. We just have to respect the rules of a fraction. The rules of a fraction are that the denominator is never allowed to equal 0. But I also want to clean this function up. So I'm going to factor the numerator. I see a GCF of x, leaving behind an x minus 2. I notice the denominator, x squared minus 4, is a difference of 2 squares. So I'll factor the denominator, x plus 2x minus 2. Hey, check it out. There's an x minus 2 on the top and bottom of this fraction, so they're going to cancel out. Whee! This thing is going to clean up to x over x plus 2. But you have prior knowledge. This is not what your function actually is. This is just what your function behaves like. No. This is what your function actually is. And you see, this had two numbers that would have disrespected the rules of a fraction. Two places where our pig would have squealed because the bottom of this fraction would have equaled 0. Those two places are going to be at x equals negative 2 and x equals positive 2. So I can't have x being negative 2 or x being positive 2. Those are both problems for me. So the domain of this function is actually a string of unions. Negative infinity up to negative 2, hop over negative 2, negative 2 to positive 2, hop over positive 2, and then head towards infinity. Because I crossed this x minus 2 off the top and the bottom of this fraction, this graph would have a removable discontinuity at x equals positive 2. Removable because we literally removed the factor from the function that x plus 2 was an issue for. But just because it's removed, it doesn't mean it's allowed now. No. It is still a problem, and that's why we still have to include it in our domain issues. Okay. And how about number 8 from that quick review as well? I know I'm going out of order, but who cares? This is my ship. I'm driving it. Let's see. This function is x squared plus 1 over x squared minus 1. All right. Monkeys screaming, throwing poo ensues, right? I mean, we see things that factor. They're in the denominator of fractions. We've got freaking radicals. Oh my gosh. It's okay. I want you looking at all these structures one at a time, approach them one piece at a time, and then just make sure we respect all the rules. First, numerator. Okay, there are no rules about the numerator of a fraction. It could be any number they want. But there's a radical up there. All right, the only thing that we have to make sure of is that the radicand is greater than or equal to 0. If you subtract 1 from both sides, what you get is a ridiculous statement that x squared is greater than or equal to negative 1. Well, of course it is. Everything squared is greater than or equal to negative 1. The smallest thing that x squared could possibly be is 0. So as it turns out, this thing up here, we can ignore it. It's doing nothing to the domain. Now, it's changing the way the function looks, yeah. But I'm going to be really right now, I don't care. I just want to know what kind of numbers are a problem. The domain of this function is not affected at all by our numerator. So let's look to the bottom. We got to make sure we don't break the rules. Aha! There it is, a difference of two squares. You see x squared minus 1 is x plus 1 times x minus 1. And our pig would squeal if either one of these parentheses turned to a 0. So what we know is that x can't be negative 1 because of that, and x can't be positive 1 because of that. Remember, positive numbers allowed, zeros on the bottom, not. Our domain then is very similar to this one, but instead of hopping over negative 2 and positive 2, I would hop over negative 1 and positive 1. Now, that radical on the top, if it had said x squared and instead of plus 1 it said minus 1, okay, that definitely would have changed our domain. So what would we have done then? Well, we would have factored it, okay? And you know what? Instead of saying it, why don't I just show you? I'm pretty sure we've come across one of these before, but hey, let's just go ahead and get it on there. Let's just say that we had this. We'll worry about the fraction here in a moment. I need more paper because it's getting all bumpy because my table's not smooth. There we go. What would we do? Well, we have to respect the rules of a radical, and the rules of the radical are that the only numbers that are allowed to be under it are 0 and bigger. So we would say x squared minus 1 greater than or equal to 0. Oh, look, a quadratic inequality. You see, those came up in the chapter A and B material. They're a pretty big deal when you start talking about domains of functions. This factors. And this is where we would set up our sign diagram to figure out where our quadratic was positive or 0. Our critical values are negative 1 and positive 1. We're testing all three zones, trying to get values that are greater than or equal to 0. So 0 and positive is allowed. Let's see. We grab a number from to the left of negative 1, like the number negative 2. Negative 2 plus 1 is negative. Negative 2 minus 1 is negative. And the product of two negative numbers will always be positive. Okay? Test the number between negative 1 and positive 1, like 0. 0 plus 1 is positive. 0 minus 1 is negative. The product of one positive and one negative will always be negative. And lastly, numbers to the right of 1, like 2. 2 plus 1 is positive. 2 minus 1 is positive. I think it's pretty obvious what's going on there. Just like that. So this thing's domain, pointing at the wrong thing. This thing's domain is negative infinity up to and including negative 1, union, beginning at positive 1, including to infinity. There it is. What if, though, I was going to do questions from the book, but I've just gone off the rails here, and I love where it's taken me. What if I throw that x squared minus 1 down here? I mean, we just saw that the domain of that radical itself is this. So does this still work? No, pigs are squealing. Why? Because we have to respect the rules of this fraction bar. Cannot have 0 on the bottom. So instead of saying x squared minus 1 is greater than or equal to 0, we would have just said x squared minus 1 is strictly greater than 0. The equal to 0 is no longer allowed. Same sign diagram, same critical values. Only difference is now we cannot have the brackets on our 1's, so the domain then would have been negative infinity to negative 1 non-inclusive. Hop over it. To 1, hop over it. to positive infinity, like that. Alrighty, and let's see if I can come up with something even more ridiculous for our last example. Okay, I got it. Something even more ridiculous. Let's put a radical up top, and I will stick with x squared minus 1 because we already know how that one's domain is going to be handled. And then I'm going to write this. I don't know. How about minus 3? That feels good. Okay. If I hadn't put that on the bottom of the fraction, we would have had this example right here, and this would have been the domain. And the reason why I'm doing that is to keep the video notes for this quick practice lesson a little bit shorter. This is the domain of our numerator because it's the top of the fraction. So for this part, we already know because of the last two examples that we're going to be dealing with the numbers from negative infinity to negative 1 inclusive, and also from 1 to infinity. But don't let these pigs squeal. You see down here, x minus 3 is not allowed to equal 0. So if you add 3 to both sides, what you're going to get is the statement x cannot be the number positive 3. And all the rules must be respected. So this radical is dictating that we only allow these numbers to the left of negative 1, including negative 1, and these numbers, the numbers to the right of positive 1, including positive 1. And the denominator says, oh, but don't you let x be 3. That's within this set of numbers. So what do? We just rewrite this set of numbers, but hop over the number 3. So the domain says negative infinity to negative 1, inclusive. Then hop all the way over to positive 1, inclusive. Go up to 3. Oh, but x can't be 3. Sorry. However, we can just hop right over it with that union symbol and then pick our crap back up and keep on going towards positive infinity. And now we're ready to rock and roll. Hopefully, that clears up some mysteries about how to find the domains of functions that have radicals, fractions, and or both. The only thing that I didn't really show you is fraction underneath a radical. You know what? We'll let the notes go a little bit longer, and I'm going to show you fraction underneath a radical just in case. I wouldn't want anybody to say that they weren't prepared. So let's take something we already know and love. How about, I don't know. Oh, I'm feeling, you know what? Let's just do the one we just had. Was it plus 3? Minus 3? I don't remember. Minus 3, like that. Okay, it's a slightly different animal now. Right off the bat, I see a fraction bar, and I know that the denominator cannot equal 0. Therefore, right here, this little thing right here is already telling me I know x cannot be the number negative 3. Now, I know that x squared minus 1 has critical values. Critical values at x equals negative 1 and x equals positive 1. So this one's slightly different. This is probably even a little bit more advanced than anything you would have to worry about in this material. But hey, you know, like I said, your boy, and I want to make sure that you're super prepared. So what do? We actually treat all 3 of these things as critical values. And we just make sure that this thing underneath the radical is greater than or equal to 0. Because that's the rule, right? And rather than trying to solve, you know, for x or anything like that, what we do is we put our 3 numbers on a sign diagram. And we just check the zones for positive and negative. Those three, those three values are +1, -1, +3. Same ones we were dealing with before. -1, +1, +3, picture not drawn to scale. And we just check the three zones, and we make sure that we respect all the rules. But you know what I'm going to go ahead and do? I want to go ahead and show you that 0 is allowed, right? So the numbers -1 and +1 will be part of our answers. But the number 3 is not allowed because that would have you dividing by 0. There. Now let me check those zones. Let's grab a number to the left of -1, like -2. That's going to give me a negative, and a negative. Negative, negative over negative. The numerator of that fraction would have been positive. The denominator would have been negative. That would give me a negative overall result, 3 negatives. If I grab a number in here like 0, 0 plus 1 is positive. 0 minus 1 is negative. 0 minus 3 is negative. That's going to give a negative number divided by a negative number, which will be a positive result. How about a number between here, like 2? 2 plus 1 is positive. 2 minus 1 is positive. Okay, the numerator is positive. 2 minus 3 is negative. A positive number divided by a negative number is negative every time. And no, you cannot just assume it'll oscillate. You do need to check. Let's grab a number over here like 4. 4 plus 1 is positive. 4 minus 1 is positive. 4 minus 3 is positive. Of course, if they're all positive, everything is positive. So remember, zeros were allowed. Negative values overall were not. So our overall domain is -1 to +1, inclusive because 0 was allowed. And then from 3 to infinity. That is an advanced question. And I hope that everything I've shown you today has cleared up some mysteries, and I hope that this one hasn't boggled your mind, because it is more advanced than you need. And after this, I'm hoping that everybody has this feeling. I know I certainly do. Thanks, guys.